A lot of you are working really hard at this, and you guys are probably going to do well on the test. But if you're sitting around waiting on me to do the answers for you, that's passive learning. It's not active learning. Okay? Active learning means you're trying to get it done for yourself, trying to figure out the answers for yourself, trying to solve the problems for yourself, and getting help only when you need it. Okay? That's building mental muscles. And good for you if you're doing that. Okay? All right. I think most of you got everything up to just the last little bit there. And I'm going to go through the steps for you really quickly then. Hydrogens have 1 valence electron. Carbons have 4. Is that what you want when you keep moving like that? Oh. I'm playing. I know. All right. So let's share some electrons now. Now, if when you share your electrons, if you don't have the right number of electrons on each atom, you know you've messed up somewhere, and you go back and try something different. Okay, there's nothing wrong with getting this part wrong to start with. What would be wrong is if you leave it like that and not fix it when you realize, wait a minute, this atom has 7 electrons and that one has 9. We've got to get them all right. Okay, so this gives both the hydrogens 2 electrons, and hydrogens only want 2 electrons. Okay, so now we can. So to get carbon and oxygen to have the 8 they want, we got to share 2 electrons between them, or 2 sets of electrons between them. Okay. So now if we take this then and draw a Lewis dot formula where we squeeze the shared electrons between the atoms, that means between the carbon and the hydrogen we're squeezing 2 electrons, and there are 2 of them. But between the carbon and the oxygen we're squeezing 4 electrons. Okay? Andrew, would you shut that door over there for me, please? And so the oxygen then has these 2 lone pairs over there we can't just throw away. In the Lewis dot formulas, we've got to keep those. Okay? Now we're going to look and see how many sets of electrons are there around the central atom. Okay? Well, this is a set. It's a shared pair. This is a set, a shared pair. And here I've got 2 shared pairs that make up 1 set. Doesn't matter how many electrons you're sharing between 2 atoms, they will make up a set. Okay? So that's 3 sets. So if you don't remember from the last unit what kind of arrangement will let you put 3 sets of electrons as far apart as possible, you need to get out your Unit 3 handout. Get out your Unit 3 handout. Okay? And you're going to look and find the electron pair shape, the general electron pair shape in the chart that I gave you. And the chart shows that it's this kind of shape where these angles are 120 degrees apart that gets them as far apart as you can get them. Okay? Now, that's not 120 degrees, folks. I'm sorry. No. That's not 120 degrees. Okay? So, these don't work. This is 120 degrees. Now, I don't expect you to be an artist, but I need you to come up with a reasonable 120 degrees. Okay? Alright, so we're going to put our sets of electrons on there. Now, 2 sets, or 2 arms, have just 2 electrons. But 1 arm has got 4. So one of these arms I need to put 4 electrons on. So that's our...
Doesn't matter what arm you put 4 on?
What's this called?
No.
What kind of shape is this?
This is trigonal pyramidal. So this is a trigonal pyramidal electron pair shape. I'm sorry, you're right, trigonal planar, not pyramidal. Trigonal planar electron pair shape. You're absolutely right. Yes. Yeah. Okay. All right, so then the next step is to take and redraw this same thing. Put the electron pairs on there. But now we're going to go back and look at which of these sets of electrons are shared. In this particular case, all of them are shared. If they're not shared, you're not going to replace them. Now, if they're lone pairs, you don't replace them. But in this case, they are all going to be replaced. So the two hydrogens here are sharing just two electrons, so we need to put those here and here. And then, yeah. So this set has 4 electrons, so this set of 4 here needs to be replaced with the oxygen that the carbon is sharing those electrons with. Okay? Alright, so there's a molecular shape. This is still trigonal planar. So this is a trigonal planar molecular shape. Okay? That's what we did in the last unit. Now in this unit we're learning how to figure out, well, is this molecule polar or not? So we got some more work to do. In this case, this is like in your Unit 4 handout, where you've got a trigonal planar arrangement with bonds that are nonpolar and polar. It's an uneven arrangement here. Okay, you've got electrons all the way around, but these or atoms all the way around, but these atoms are different. Okay, so let's take a look here at what this means to us. So the hydrogen to carbon bond. Let's see, we figured out on that previous sheet we had that the electronegativity difference between carbon and hydrogen was 0.5, didn't we? Okay? So the electronegativity difference between carbon and hydrogen is 0.5. That's the electronegativity difference for the carbon to hydrogen bond. Okay? Now we need to know the carbon to oxygen bond. That one we don't know yet. So we need our periodic table with oxidation numbers. Oxygen is 3.44 electronegativity. And carbon is 2.55. And we're going to subtract.
So we don't draw any more, there's no more
You don't, no, we could actually work with this right here to figure it out. Okay? So I think this comes out to be, what is it, 0.89? So that's the electronegativity difference for a bond between oxygen and carbon. Okay? Alright. So this bond between oxygen and carbon is clearly polar. But this one is just barely polar. So the question is, are they helping each other or canceling each other out? So are these bonds, this one and this one, helping each other or canceling each other out? So if they're kind of running into each other, they're canceling out. If they're pulling in the same direction, they're helping each other. Okay? So let's use arrows to figure that out. The carbon has a smaller electronegativity than oxygen. Oxygen is more electronegative. That means the electrons are spending more of their time there. So we're going to have our arrow drawn toward the oxygen. Okay, going back and looking where we calculated the electronegativity for a carbon-hydrogen bond, we can see that carbon has a higher electronegativity than hydrogen does. So the electrons are kind of tending to spend more time in that direction. Okay? Alright, does that look like they're helping or canceling out? I would say, alright, think about rivers. You got streams coming into a single river and flowing. So these are kind of helping. Okay? Okay, so the question Carolyn was asking me is, don't you add this number right here and this number together? Well, that would be true if they were on a straight line. But these are not on a straight line. Okay? So what we really have to do to figure out how much they add together is something called vector addition. For most of you, you don't get into a math class where you ever deal with vector addition. If you take physics, you'll get a little bit of that. But basically, what I want you to know is they're helping each other. And if they're helping each other and they're both pretty close to being polar, or they are at least one of the bonds is definitely polar, then the overall molecule is going to be polar. Okay? If they're not helping each other, then they're kind of tending to cancel out. All right? So without doing vector addition, which is a much more complex process, okay, then just you have to use good judgment about whether they're helping each other or not. Does that make sense? Yes.
So the one on the bottom, the H with a blank, that's not supposed to be turned, it's supposed to be an error.
Right here?
But the left one.
What?
The left one. Yeah.
That's an arrow. And they're kind of going this way and helping out the
It's
oxygen.
not supposed to be a triangle.
No. No, it's not a triangle. Okay. Now, right. Got it? Now you and CJ should have the easiest time understanding this. Okay? Cause you know, you're right. You are right. I am sorry. I did leave you completely out of that. I'm sorry.
Yeah, unless you don't play with that.
Okay?
It's do you. Ain't don't you. It's do you.
Do you what?
You said down.
You want your hand?
He's trying to correct to the grain.
Okay. All right. And he said he wanted a teacher too, didn't he? All right. Okay. Listen up. All right. If two offensive linemen are blocking this guy right here from these two angles, which way are they pushing him? If they're both hitting him from those angles, which way is this guy going to go? Which is in the same direction as the oxygen, isn't it? So they're helping out the oxygen.
I mean, I get what you're saying about which way they're pushing it, but I don't know how that relates to which way the arrows go.
Okay.
The arrows go towards-
Okay.
That's me on the right.
I'm the old. I'm the egg. Right.
Down there.
You did.
Is it D-A-R-E-I-L-L?
Oh,
Okay. Okay. All right. Okay.
that is hilarious.
So y'all are taking on Daryl there, boy. I'm telling y'all are going to block him out. If you hit him like this, which way is Daryl going to go? That way, which is the same direction as the oxygen is, isn't it?
I'm going forward, man.
Yeah, I know, but they're pushing you. You get the point.
You get the point.
Okay.
I ran drills.
So if they are acting in such a way that they support this, they're all helping each other. Okay? Got that? All right. See? You guys do physics on the football field all the time and just don't even realize you're doing it.